Thank you very much. I'm really honored, or nowadays you say humbled, to be invited here. And I thought that the reason that I was invited, I tried to find a reason I was invited because I couldn't figure it out. And then I looked around the room and I thought, well, maybe I'm the oldest one, the oldest list person that could be found. And it turns out that's not true. And I won't embarrass the two people who are older. Um, Maybe I'm the one who has used Lisp the longest. I think I first started using Lisp in 1971, so that's probably not the oldest. I don't know. Anyone before 1971? There. Okay. So there's no good reason for me to be here, I think is the answer. Now, Didier asked me to give a keynote about whatever I wanted. I'm not going to talk about woodworking. But I will not talk too much about Lisp, although there is, interestingly, I found there's some interesting overlap with Marcus's talk. There are a few touch points where we talk about the same things and we disagree, but that's okay. And of course, during his talk, I was furiously writing new things. Let me say also that I didn't really, as Pascal said about his letter, I didn't really have the time to make this short. So I'm planning to go through lunch and afterwards, you know, the way in medieval monasteries, they would have someone speaking while the lunch was done in silence. No, I'm not going to do that. All right, so let me tell you a little bit about my personal story, which might be interesting to those younger people here. My father was a physicist and had access to a time-shared computer, which in 1967 was a very rare thing. Not many people had access to computers, certainly not people my age. So I was 12 years old in 1967. And we had a teletype. So imagine yellow paper printing at 10 characters per second. And we were connected to a thing called an SDS 940, which was actually a pioneering time-sharing system, with an interactive language called CAL, which was based on JOS or Telcomp, same family of languages, which much later led to languages like Python. Not anywhere near as powerful, but very interactive. So that was the first interesting thing, that it was an interactive language. So people ask me typically, because of my age, you probably started on punch cards. And actually, I never used punch cards, never. Punched paper tape, yes, a little bit in high school, but that was the end of that. Let's see. So when did I learn Lisp? I learned Lisp, I think it was in 1969. I was at a high school which had a connection to Dartmouth timesharing, which was an innovative system at the time. Their philosophy was that every undergraduate, not just math or computer undergraduates, every undergraduate would have access to a computer. And this was done by Kemeny, who later became president of Dartmouth. So this was a revolutionary thing. And on that system, Dartmouth didn't have many graduate students, I guess, but they had some. And one of them had written a Lisp interpreter. And so here we were in a high school having access to something that was very rare again at the time, a Lisp interpreter. And being, you know, hackers and nerds and so on, we did things like disassemble. We didn't actually have access to the source code of the thing, but we wanted to know how it worked. So we disassembled the source code in the debugger. And later we took a field trip to Dartmouth and had the right to go through their corridors. In those days, when you wrote code, typically you'd write it at your terminal. This is non-punch card, and then print it out on the line printer. So there'd be these line printer listings about this thick of code. And they were recycled regularly because every so often, you know, you wanted an updated version, because you'd write annotations in the old version, and then you'd want a new version every week or two. And so in the corridors at Dartmouth, there were these listings lined up, and you could take, they were going to be taken by the recycling people. So we take one of the early examples, by the way, of recycling. No one recycled at that time. So we'd take those things and take them back home and study them, and say, that's how it works. So we learned a little bit about how it was implemented. I joined the Maxima. I was very interested in Lisp. I played around with Lisp. I wrote some what you'd consider trivial programs like symbolic differentiation, very easy. Where I learned the first lesson of symbolic algebra, which is that it's not the differentiation that's hard, it's the simplification. So you'll see some examples of that problem later. Over the summer, I managed to get myself into the Maxima group at MIT, which is, it turns out, the real reason I was invited, because I was involved with Maxima, and Didier wanted someone to represent that group. I was the youngest on the group. There were professors, there were graduate students, there were undergraduates, and here I was, the high school student who was on the team. And some of my code from 1971 still survives today, by the way, in the open source Maxima project. It's terrible code, but it still survives. I was also an early user of Emacs. I think that started, or the predecessor of Emacs, which was called TCMac in 1975. And then, of course, Emacs Lisp later, which is still my standard place for fooling around. People typically have their standard place for fooling around. Some people use R, some people use, I don't know, Python. I use Emacs and Emacs Lisp for finger exercises, not for serious stuff, but for finger exercises. So I thought I was really exceptionally young. I was very proud that here I was at age 15 working at a computer lab at MIT, and I must be really smart and all that. And then I discovered that there was a fellow who was 10 years older than me, named Peter Deutsch, who had, not only had he been working on computers at MIT as a high school student, but he had written a Lisp implementation when he was 17, PDP-1 Lisp. He had also contributed to the SDS 940 system, which I was a user of. So and I talked to him on the phone, and later he worked on Smalltalk and on GhostScript. So I talked to him on the phone, and we had a lot of parallels in our personal histories. His father was a physicist, my father was a physicist. We went to the same junior high school, the same high school. He didn't go to MIT, he went to Berkeley, I guess. But it was funny to hear these things, but he was 10 years older. So much for the pride of being the youngest. Nowadays, I'm a product manager at Google. I'm sorry, not nowadays. I changed to so I became a product manager at Google many years later. And you say, well, how did you become product manager? You'll hear about that later too. And the interesting thing there was I was in the group that came from ITA Software, and we have two representatives of that group here today. We have Doug Katzman and Martin Krakauer. Now they represent the largest Lisp system ever, and I represent, I guess, the oldest Lisp system that's still running. So QPX is the system behind Google Flights. Not only is it a huge, complicated system, but it also surely consumes more CPU cycles than any other Lisp program ever has. It runs on multiple, I don't know, I'm still not allowed to say how many CPUs it runs on, but a very large number. Every time you do a query on Google Flights, you're running QPX behind the scene. Okay, so let's see, where are we now? So now that I've done all the introduction stuff, I'll talk about what my topic is. Oh, we actually got my slide on there. And now I have to figure out how to get to the next slide. What's that? Don't worry about it, thank you. So my theme is there's no joke, and I don't know how much of American culture has gotten into European culture, but there's an old joke which is, predictions are hard, especially about the future. So not very much laughter because everyone already knows the joke. But there's actually good scientific evidence for this. This is not just a joke. So Professor Howard Raiffa in 1969 published an interesting study where you ask people for numerical results, like what's the population of Australia? And you say, I want you to give me to tell me your confidence interval. What do you think is, how confident are you of this? And he says, well, I'll let you decide the 5% and the 95% intervals of your confidence. So is the population of Australia, it's somewhere between whatever, 100 million and 200 million. I have no idea, by the way. And it turns out that, so that means that 10% of the answers should be wrong. Does anyone want to guess what the actual proportion of answers that was wrong was? 50%. So people are much more confident in knowing, even when you give them a range of results, they're much more confident than they should be. And there are various other psychological issues around estimating and all that good stuff. So let's see. I'm going to skip a little bit because I'm already behind. Let's see if we can get to the next slide. Let's see.
It's fine. No, we just we screenshotted your slide.
Oh, is that what you did?
Not that fast.
I had no idea what was going on. Okay, very good. All right, well, the next, now I want you to imagine the Gartner hype cycle. How many of you know the Gartner hype cycle? Too few. So the Gartner hype cycle says, okay, here, I'll be the human graph here. The Gartner hype cycle looks like a graph like this, goes up and then down and then slowly back up. And the idea is that you have some new technology and people get very excited about it. And then they realize that it doesn't really do as much as they expected, and it's going to be harder to implement correctly, which is the trough of disillusionment. And then slowly, slowly, people figure out how to use it effectively. If there are any Mac experts, by the way, in the audience, it would be really nice to be able to see my notes and have my projection. But okay, so that's Gartner hype cycle, and we have all sorts of stories about what the hype cycle is about. People believe, so my God, how did you do that? Oh, you got your own. You got it off the web. Excellent. Well, that's where I got all my illustrations, so that's perfect. Wow, this is a great support here. So there are lots of stories about all these products and so on, and mostly business oriented. You'll be happy to know I'm not an MBA, so I'm not going to give the business oriented side of things. But one of the interesting things, so the hype cycle is published by Gartner, which is a consulting group, and people take this fairly seriously. And you can sort of map different ideas here. You have, let's say, Lisp going up, and then the AI winter, and maybe you have the plateau of productivity. I'm not sure, or maybe not. So there's a study a few years ago by a guy named Mullaney of the hype cycle, who said out of the 200 technologies, and the way Gartner does this, by the way, is that every year they publish this graph with technologies at different places on the cycle. So they say, oh, Lisp is here and Emacs is here or something. I love Emacs, but there are not many of us. So out of the 200 technologies that were ever listed on the hype cycle, only 50 reappeared the following year. So even this wonderful predictive thing turns out not very predictive. Now, what are some of the failures? You may be familiar with some of the failures. Okay, now I can't even get onto my Emacs screen. Here we go. So what are some of the failures? Do you remember desktop Linux? Everyone was going to be running Linux, right? Very few people run Linux on the desktop. Open source, on the other hand, has been a surprising success, but not Linux in particular. Why? I don't know. RSS in the enterprise was supposed to, so anyone here remember RSS? Well, you know what RSS is, right? For feeds. Well, this was supposed to become an enterprise technology. Mesh networking. Mesh networking still isn't working. I mean, it was very exciting. People thought it would be great. There are lots of military applications. I know some guys who are working on mesh networking for tanks. So the tanks set up a mesh network in the field, works very well. But mesh networking in the home, it's sort of not working very well. Fifth generation computing. Does anyone remember the fifth generation computing project in Japan? So it was based on Prolog, and it crashed and burned. As far as I can tell, it led to no interesting technology. Although it did result in a lot of education happening. So a lot of these things, they have their side effects, even though they don't have their effects. Oh, and so years ago, I worked in Europe, in France, and there was an international consortium. There's funding for international projects at the time called Esprit, Esprit in English, I guess. So Esprit was this fantastic thing. They sort of poured money into projects, and they got some interesting results. Not as many as you might like. At the same time, in the US, there was also a lot of funding for these things. But in my opinion, the key funding, the thing that actually made the difference between the computer science communities in Europe and in the US was the ARPANET. The fact of having a fast network that connected all the researchers. At the time, I was working at Bull, which is one of the largest computer companies. in France, or the largest computer company in France, except for IBM, of course, which is the largest computer company everywhere. But the Bull Research Lab had a network connection. It was a Usenet connection going through Amsterdam at 64 kilobits per second for the whole research campus of Bull. So networking, I think, would have made a big difference. So with some of our colleagues in the Esprit project, we were collaborating on a project. I think they were we had one collaborator in Denmark, one collaborator in Italy, and we would send messages, of course. The messages would take easily 24 to 48 hours to arrive because of buffering. So that made a huge difference, but I'm off my topic. Many other things have not happened the way we expected. Who remembers micropayments? So the idea was that why would you have advertising paying for everything? Why not, when you use a service online, whether it's Facebook or Google, instead of being the product, as the expression says, why not just pay for the service? Every time you use something, you pay a penny. People were very excited about this. They thought, well, this is how we're going to fund work on the internet. You're going to pay your newspaper by the article. You're going to pay Google. You're going to pay Facebook. All these guys, whoever. 6 Degrees. Oh yes, that's another failed one. Who remembers 6 Degrees? 6 Degrees was a predecessor of LinkedIn. Had exactly the same idea, exactly the same business model, and they failed. But who's going to pay for the micropayments? So the idea was we developed technology so it's very cheap to send very small amounts of money. Sort of the opposite of the crypto systems, where you spend a lot of money to anyway, and pollute the environment and all that. But so the idea was to have a cheap way. That went nowhere. There was good technology around, wasn't adopted. Why not? I don't know. Actually, I do know, which is consumers don't like it. Consumers like to know how much they're going to pay in advance. They much prefer subscriptions. So you notice that I don't know what the phone plans are like these days in Europe. In the US, they're all subscription based. They're not phone call based. I think in Europe, there's still many plans that are phone call based. You pay 20 cents per call or whatever. Is that right? I don't even know. Consumers prefer subscriptions. The same thing happened in the newspaper space. The New York Times does not charge you 5 cents per article. They charge you whatever it is, $10 per month, and you can use as much as you want. So that's a psychological one, not a technical issue. I won't go through more examples. I think you get the idea. Now, in the US, again, culture has become international. We tell the story about the California gold rush. So the California gold rush was in, I guess, 1849, and gold was discovered on the property of a man named Sutter. And people rushed in from all over the country to exploit this. And they were miners, and they were looking for gold. Few of them actually found gold. But the standard story says that it wasn't the miners who got money, who got rich. It was the providers of services. So you may have heard of some of them, like Levi's. Levi's provided clothing to the miners. The bank, what's called, I have it somewhere here, Wells Fargo was founded to service the gold miners. Armour Meat, which is a very big meat packer in the US, he made a little bit of money on the gold fields, but then he left and sold meat. So he didn't actually make his big wealth from the gold. Another guy who we haven't heard of now is named Brannan, who sold mining equipment. And his slogan was, during a gold rush, sell shovels. So what's the lesson for us? That you should be developing tools, of course. But I don't think that's true, except for Intel, which of course is making a lot of money off everything. You don't make a lot of money by developing compilers. I mean, I was in the compiler business for a long time. You don't make money developing compilers and interpreters. But maybe money is the wrong criterion. Maybe success isn't about money. Maybe it's about adoption. So let's talk about Lisp. Has Lisp been successful? What does that mean? What does success mean? Certainly, no one's really made money off it. There have been several bankruptcies around it, but no one's made money off it. How many of you know Greenspun's 10th rule? Oh my God. Okay. too many people, common culture here. But for those who don't, any sufficiently complicated C or Fortran program contains an ad hoc, informally specified, bug-ridden, and slow implementation of half of Common Lisp. So many systems that have extension languages have this sort of half-assed extension language that looks like Lisp. I would claim that we're exaggerating a little bit, because we Lisp people tend to call every dynamic language Lisp-like. So they're not really Lisp. You may think of them as a mini Lisp, but they're really just whatever is easy to implement. And some languages actually, though, do claim that heritage. R claims to be inspired by Scheme. But if you look at the semantics of R, you'll say, oh my God, you show this to Jerry Sussman, he's going to die. Because it's sort of taking Scheme mechanisms and turning them on their head and using them as assembly language, and you do weird things with scopes. But it is true that Lisp, as Marcus said, has been used in many surprising places. You say, you look at this language, do you expect that this language should be used for text processing? Say, no, this doesn't look like a text processing language. Does it look like a 3D modeling language? Well, it's the extension language for AutoCAD. So it is successful in some sense. On the other hand, some other claims that are made by some people, like Lisp has something to do with object-oriented programming, is complete nonsense. In fact, of course, there was an object system in Lisp, but it was developed many, many years after Simula, Simula 67, Smalltalk, and so on. So it was the object orientation was a copy. That's okay. It's good to copy good ideas. Conditional expressions. Everyone thinks of conditional expressions as being uniquely Lisp-like because Fortran doesn't have conditional expressions, or C doesn't. Well, C does, I guess. C has the ternary operator. But in fact, conditional expressions. Who knows the first language that had conditional expressions? Conditional expressions meaning expressions that have a conditional in them and return a value. Algol 60. Algol 60, yeah. And Lisp was about the same time. So they came at about the same time. In fact, Algol 60's conditional expressions were inspired by McCarthy's Lisp. CPL at Oxford was also had conditional expressions. See, my notes here say I'm 35% of the way through my talk, and I'm more than half of the way through my time. All right, so let's, can you find the time cover page about the internet?
I'll try.
This is great. This is, real-time illustrations.
We're a dynamic language.
What's that?
We're a dynamic.
We're a dynamic language, right? So it's the cover image of Time magazine in 1992, I believe, with The Internet, it was called. So here we are, Time magazine, mass market magazine, announced that the internet was the new trend in 1992. So this was, I guess, 1 year after the HTML and so on, where the web was announced. Is this because in 1992 there was a huge surge of users? No. And my next two slides, which are invisible, one of them shows the number of internet servers over time. And you want to see somewhere in there, you want to see an inflection point where it goes from this to this. What actually looks pretty much like this. It's pretty much smooth with a slight decrease over time as it saturates. So there's no big inflection point. If you look, there we go. Wow, amazing. So the strange new world of the internet. Time magazine recognized that something was going on, but there was no clear inflection point. And if you look at the historic trend of the number of users of the internet, that only took an inflection point about 5 years after this article. So maybe they're very good predictors, but I think they were lucky. Now, what are some things that were predicted in the past that did come true? So here we are at the AI lab in the 1960s and 1970s. The AI lab at MIT, very famous place. A lot of the famous hackers came out of that or created that environment. We had magnetic tapes of satellite imagery. So think Google Maps. We had a feed of AP News. Think Google News. We had email, of course, internal email. We had distribution lists. We had real-time chat. Actually, we had two different kinds of real-time chat. We had graphic displays fairly late, started in 76 or so. We had a local area network. We had a wide area network, the internet. We had blogs, although they weren't really blogs, they were files, but since there was no security on the system, everyone could read everyone's files. And if someone pointed you to a file, said, here's so-and-so's diary, which he intentionally made available to everyone. There was a crazy guy, I can't remember his name, but I think someone here does remember his name. He had every day his entries about his love life or non-love life and his depression and threats to commit suicide. Amazing. I mean, so here we had blogs in 1977 or so. We had structured documents, so think HTML. Scribe was invented in 1980 by Brian Reed. 1980. So HTML, why was HTML needed 10 years later when we had Scribe? Now, all of this was done on a computer of 256K words of 36 bits, shared among 30 to 60 simultaneous users. Nowadays, you buy a laptop that has less than 16 gig, you say, it's not a very good one. But a lot of good stuff was done with very, very limited resources. So what happened in the meantime? Oh, and we had amazing tools too, software tools. So on the ARPANET, the wide area network, we had the data computer. I don't remember, I should have looked up the capacity of the data computer. The data computer must have had a capacity of something enormous, like a gigabyte or something like this. And it was shared by everyone on the ARPANET. Of course, nowadays the gigabyte, who's seen the Google internal video which escaped, which starts with, I just want to serve 5 terabytes. And the system resource engineer that this software engineer is talking to says, 5 terabytes? I can't even count that low anymore. It's actually a very good video. If you take that quote and look on YouTube, you should watch the whole thing, 3 minutes. We had remote job entry. We had Telnet. We have FTP. So all this in 1969, but it still took until 1991 for the World Wide Web. We had all of the components. We had structured documents. We had networking. We had, now it was very slow and very limited. So the ARPANET only covered a few dozen centers, but we didn't have anything like the web. No one had documents that could link to other documents, hypertext. And hypertext had been invented long before. I mean, Ted Nelson was around, and before Ted Nelson, there was, I forget who. But other things were predicted to be impossible at the time. Now, in particular, everything that's NP-complete, everyone knows that there's never going to be progress in solving NP-complete problems, right? If it's NP-complete, you give up, you forget about solving the problem. Well, A, people started developing very, very good approximation algorithms, and B, they started developing very good software to solve problems even without approximation. So the 3 satisfaction problem, 3SAT, how many of you are familiar with 3SAT? So if you've done any computer science formalism, you know that determining whether you can assign variable values, true or false, is Boolean, for a list of clauses, so an or of and or an and of ors, it's dual, it's the same thing. To make it true, that's known to be an NP-complete problem. And so people say, well, that means that 20 clauses are going to be exponentially worse than 10 clauses. There's no way that anyone's going to do 100 clauses. Well, routinely today, people do thousands, 10,000, I don't even know what the state of the art is. You probably know the state of the art. Tens of thousands, hundreds of thousands of clauses of 3SAT problems, and they use them in practice. So there are some surprises in the positive direction. Everyone thought natural language understanding would be unsolved for a long, long time. And speech recognition. Well, it took a long time. Speech recognition sort of worked in the 80s and 90s, sort of. But now it's amazingly accurate. We have, of course, with LLMs, large language models, we have production of text, which is very fluent. I don't think anyone predicted that even 5 years ago, that it would be this fluent this quickly. Now, of course, it's often spouting nonsense, but it's very fluent. That is, it sounds like a person. But people spout nonsense too, right? And in fact, I'm going to come back to that a little bit. So let me now go to Maxima, which is why I'm here, I guess. So I'm stuck with talking about maxima. Search on Quora for Quora Macrakis, if you can spell that correctly, um, quartic formula.
I can't do that, Dave.
I know it's there. So when the symbolic math, we're going back to symbolic math, to maxima now. So here we are, a bunch of computer scientists, the notion of computer scientists doesn't really exist, mathematicians, engineers, developing symbolic algebra. You say, this is fantastic. It started out as an AI problem. So when Joel Moses wrote his thesis on symbolic integration, that was considered AI. It's not considered AI anymore, right? But partly because there are algorithmic solutions to part of it, like the Risch algorithm, partly because it's a large pattern matching problem. You can go to the tables of integrals and you have 2,000 integrals and you just do pattern matching. But at the time it was considered AI. So because it's something that clearly requires human intelligence, like chess playing. I mean, if you can play chess or Go or something, then you must be intelligent. So if you can integrate, you must be intelligent. So let's solve this toy problem of integration. And Joel Moses, in fact, made real progress on integration. And then there are various algorithmic developments in Maxima, like polynomial factorization using the good algorithms and so on. And then people started to think, maybe this thing is actually useful. Not that one. So it's on Quora. Okay. And it's a big formula. You'll see there's a big formula. This has been amazing. I wish I had you with me all the time. So you say, oh, maybe this thing could actually be useful for real engineers and scientists to do their mathematical work. And of course, being engineers and scientists, we thought, oh yeah, we won't think much about the user. We won't actually study what users do in their real life. We'll just imagine that they're doing what the textbook says they should do. And the textbook says, oh, I want to calculate some eigenvalues. Well, that's you generate the characteristic polynomial and then you solve it for its roots. Well, that's a terrible way to find eigenvalues, by the way. Maybe I want to solve a quartic equation. We all know that there's an explicit formula for the quartic equation. Not for the quintic, but for the quartic. Quartic, yeah. And so you say, let's program this into Maxima. So now you can say solve. It looks like magic, right? You say solve, it says x to the fourth plus x to the third minus 25 times x plus 23. That's not it either. But it looks nice. Are you looking on Quora? Site:/Quora.com. Macrakis, quartic. Okay. Anyway, so it turns out that even with, so you say, well, this is great. It's symbolic solution, right? So if I have symbols on the input, I'll have symbols on the output, and I'll be able to, everyone thinks symbolic solutions are so much better than numerical solutions because you can get some intuition. You look at this thing and say, oh, I see. When A gets bigger, then the overall thing gets bigger. So symbolic solutions are really wonderful. Turns out, though, that if you solve a quartic, even for numerical coefficients, the result is so complicated that there's no way of interpreting it usefully. So if you take the quartic formula and plug in the coefficients of a very simple equation which has a root at 1, the root at 1 is this messy combination of radicals, and there's no easy way of determining that it's 1 except by evaluating it numerically, which is what you were trying to avoid in the first place, right? You said, I want the intuition of what does this look like? What does the answer look like? Well, okay, so it turns out that the better way to solve a quartic is by numerical techniques. That if you use a polynomial solver, and the polynomial solver, you know what? Polynomial solvers work for 30-degree polynomials too, not just degree 4. And they're accurate and they're fast. The other problem with the symbolic solution is that it's not numerically stable. It has a tendency to have subtractions of nearly equal things, so you start getting errors and so on. And taking a symbolic answer and making it numerically useful turns out to be a difficult problem, which I don't think anyone's really solved so far. So it turns out in reality, and we constantly get bug notes, by the way. Oh, it's wrong because it's, sorry, that's as designed. That's right, the correct answer to the. So you discover that uh, I missed the second half of my, oh, because it's sloppy. It turns out that there are systems like Axiom, which are much more rigorous, that require you to say, this is an integer, this is a real number, this is, and so this is complex and so on, before you start doing any calculations. People hate, well, their users love them, but Maxima users tend to hate that sort of thing. They say, just multiply the damn thing out. I don't need to tell you that x is real so that you can multiply out a polynomial. You say, no, x plus 1 squared. Why do I have to tell you that x is real so that you know it's x squared plus 2x plus 1, right? It doesn't matter. Now, you say, oh, well, Maxima maybe as a symbolic system that was a failure. And of course, Mathematica has been a much bigger success. Maybe the real contribution of Maxima was the notebook interface, which we all use now in Jupyter and so on. So there it is. It's the origin of the notebook interface. Mathematica certainly has a notebook interface. Maxima had a notebook interface. But it turns out that the notebook interface was developed before Maxima and before Mathematica in a numerical system that was built specifically for engineers, which actually asked engineers what they did every day. And what they did every day was often to take formulas and plug numbers into them, and then graph things and so on. And symbolic calculation, they used occasionally. It was not a really critical function of what they were doing. They did use it sometimes, but mostly they were doing these numerical things. And they had a very nice notebook system. A system called MathCAD invented the notebook, as far as I can tell. Although I think at INRIA they may have developed some notebook technology at around the same time. So that's the failed promise of symbolic math. All right. Oh, but again, because Maxima is so messy, you can do all sorts of cool things with it. So Maxima has the notion of a matrix, of course, and we know that matrices are mathematical objects, right? Matrices are transformations of a certain kind. They have certain mathematical properties. Well, it turns out also that matrices in the Maxima setting are just an array of formulas. And if you take some of these, if you put numbers in some of these formulas and then cross-reference them, you say a sub 3 comma 3, you can do calculations on this matrix, which is really a table. And it looks an awful lot like a spreadsheet, which hadn't been invented yet at the time. And there was, in fact, a guy at MIT who used Maxima to create a spreadsheet where he was doing calculations about the Chicago Mercantile Exchange so that he could find spreads in prices for commodities and make money. And he made enough money to finance his trips back and forth to Chicago, but eventually, I guess the market somehow figured out what he was doing and he stopped making money, which is a typical thing that happens with financial innovation, right? Someone comes up with some clever idea and then the market figures it out and it's no longer profitable. I don't know how they figured it out. But here he was using Maxima as a spreadsheet before spreadsheets existed, which brings me to another theme of this talk, which is often it's not the core functionality that you've developed that matters, but the things you developed along the way. So like a cross-reference program, sounds trivial, right? You say, I have a list program and I want to calculate cross-references long before interactive systems that you say, just show me all the symbols and where they're defined and where they're used. Very useful tool until, of course, you can do it interactively, which a few years later you can do in Emacs. Maybe that's actually more useful because you can now use the same tool for Fortran or COBOL in production, as well as for Lisp, which is this obscure academic language. No eggs. All right. But it does turn out that the spreadsheet did come out of MIT, but the guy who worked on it had nothing to do with Maxima. I mean, he knew about Maxima, so Frankston. There's another sad story. Frankston developed VisiCalc, but at the time VisiCalc was developed, no one believed that you could copyright software, and no one believed you could patent algorithms or methods. And so he neither copyrighted it nor patented it. He told me that, I said, you must have made a lot of money off VisiCalc. I mean, VisiCalc, the first thing the program that everyone had to have on their computer when it came out. He said, I paid off my mortgage. His house loan. So it might have been a few $100,000. So not a large amount. And the poor guy actually works for a living these days. I mean, I think he's retired now, but he actually went to work for Microsoft for a while. Maybe he was bored. Maybe it had nothing to do with money. But Frankston is not this super rich guy because of VisiCalc. So again, what is success? Now let me tell you how I became a product manager, just of some interest. I was a company called, or an organization called the Open Software Foundation, OSF, which was the anti-AT&T and Sun system. So we were going to develop a Unix that was not subject to AT&T's licensing restrictions, which had become much more stringent. And one of the things that we developed was a project called ANDF. So ANDF was the Architecture Neutral Distribution Format. And our members, so OSF was a membership organization, our members said we need this because there are too many different architectures. We have, IBM has their hardware architecture, HP has a different one, Digital has a different one. So at the time, the x86 was not standard. Everyone had a different hardware architecture. And there's this problem: if you want to have AutoCAD on your computer, is AutoCAD going to port to all these different systems? So our users, our customers, our members said we have to have a standard way of distributing software, which might remind you a little bit of Java bytecodes. I wasn't involved in the effort at first, but when the effort was finished, at the time, for whatever organizational reason, the engineering organization didn't know anything about it. My boss, who was the head of research, said, "Tell me what this thing is and what we can do with it." So okay, so I looked into the specs, I looked into the code, I experimented with it, and I said, "Oh, this is a very nice system. How it works doesn't matter. It's not bytecodes, but it's a black box. So it's a black box that will take your C code and let you run it anywhere. You have to run an installer when you receive it, and you can run it anywhere." So remember, in these days, software was still being distributed mostly on floppies, so the small floppies. CDs were just beginning to come in, so actually the size of the program made a difference. So I looked at it and I said, "Well, this looks pretty good." And he said, "Okay, now that you understand it, I want you to explain to our members who asked for it 4 years ago, I want you to explain to them that it's done and it's now time for them to pick it up and use it." And I said, "I'm not a salesperson. I don't know anything about this." I said, I'm a research engineer." He says, "No, it's easy. Don't worry about it. Our salespeople will find the right people at each company to introduce you to, and we'll bring them in, and you'll tell them about it, and it'll be wonderful." And so, sure enough, our salespeople bring in Digital. So we have 3 or 4 pretty senior people from Digital, and I explained to them how ANDF works and how, you only need to write your program once, and then you translate it into this standard format, and then it's translated into the execution format. And now you can go to your ISVs, to your application developers, and they only have to develop the program once. And the Digital people said, "That's a very impressive technical achievement. We love it. But you know what? It's not for us." I said, "Well, why not?" So, well, at Digital, we have this philosophy that we're going to be number one in any market that we compete in. If we're not going to be number one, we're not going to compete in the market. And we want to be number one in workstations. So, okay, yes, but ANDF makes it easier for the number 2 and number 3 to compete in the market. So it is not advantageous for number 1 to support ANDF, because every vendor is going to port to our software, to our system. So, okay, thank you very much for your time. See you later. Then our salespeople brought in HP. And I explained to them, the wonderful blah, blah, blah. "I'm sorry, this technology is not for us." "Why not?" "Our philosophy is not to compete in any market where we're not going to be number 1. And then we brought in IBM. And you can predict what happened with IBM. So I go back to my boss and explain this to him, and he said, "Well, why didn't they tell us this before? How about the ISVs? What about the ISVs? They must want this technology." So you go talk to AutoCAD or whatever. I mean, it's clearly that they want this so they don't have to port things. So I talked to the AutoCAD people. It seems like really nice technology, but it doesn't solve any problem we have, because we can just all our code, we write it to be portable anyway, and we just have some conditionals. And we actually have to tune it for different platforms, because one of them has a faster I/O in this way, and the other one has different terminal I/O. So there are a few tweaks we have to do anyway. So it's not really the same software. And anyway, we just send out different packs of floppies to different people. And you know what? The real expense on multiple platforms isn't distributing it. It's the QA. We have to QA all of the platforms separately. because you never know what bugs are going to come up in the different platforms. So I'm sorry, it's no use to us. So here we were, this technology that had been asked for, that had been developed. There was a public competition for it and all this. Turns out not to be useful. And I said, well, why didn't anyone think about this before this effort? And the answer was there was no role in the organization that had that job of figuring out whether there was going to be a market for it. The roles, I mean, there was an engineering manager, there was a partner relations manager and so on, but no one actually focused on what the product is and whether it's useful and who's going to buy it and who's going to use it. No one had asked those questions about, if we develop this thing, will you use it? Now, what happened in the end with OSF? Who knows? Well, the quick answer is Microsoft. That is, all of these workstation companies, it turns out this was one of these cases where the bad technology grows faster than the good technology, and everyone started using x86. So of course ANDEF was obsolete at that point, because if you run on x86, everything's on x86. And so much for that. End of story. Let's see. I am already at 100% of my time, so I have to skip. Oh, what about logical deduction? Maybe that's a place where we can use Lisp. Do you know the paper on the British Nationality Code? Okay, Kowalski and others, yeah. So we had them present this in 1980, I guess, what it was. And we had some lawyers in the audience. So, long story short, the British Nationality Code, which is very complicated, was coded in Prolog, I think. And you say, okay, if someone is born in Hong Kong and his mother is Chinese and his father is Italian, do they have the right to reside in the United Kingdom? That kind of question. And it got all the answers perfect. If you gave it all the data, it would get the correct answer. And we had some lawyers in the audience, and their reaction was, well, that's all very nice, but it's useless. You say, why is it useless? I mean, surely that's exactly what you need. Said, no, you don't understand how lawyers work. They look at the law and they see, okay, it requires you to have been born in Hong Kong. What exactly does it mean to be born in Hong Kong? Does it mean in the territory of Hong Kong or under the jurisdiction of Hong Kong? Does it mean that you were physically born or that your birth was registered there, et cetera, et cetera? They're looking for the case that will help their client make his case. So they're looking for cases where, even though the logic is clear, the fundamental properties are not clear. And they're looking for ways around that. I'm not saying that it's useless, but it's much more subtle than one might think. And a fellow named Waddington, whom I'm sure you know as well, said an interesting thing about rules as code. He sort of backed off this notion that rules as code would just solve all the problem of legal interpretation. He says, it doesn't have the overreaching ambitions that may sometimes appear to harbor. In particular, it does not trespass into removing key interpretive functions. So, okay, what's left? So, well, yeah, you can get the hard logic, but how about the soft logic? How do you treat the soft logic, which is the hard part? Now, as far as procedures being implemented by systems, you don't need Lisp for that. There was a system called Office by Example that IBM published in 1987. There's a company called Pegasystems, which started in 1983, whose whole business is about business process management. As far as I know, they don't use Lisp, and I don't think they need to. They need some way of structured representation of their rules. Now, could they do better by having some Lisp? I don't know. Let's see. So it's been now 40 years since these rule-based systems started being used. And rule-based systems also are notorious for being hard to maintain, by the way, but that's the problem of the legislator. So now, should I continue, or should I continue, or should I bring this to conclusion quickly? Yeah, you shouldn't keep people from lunch, right? Okay. All right. So 2 more interesting things. I've been working on search for the past few years at Amazon. And now, of course, we have these fantastic things of vector similarity. So you do semantic embeddings, and you look for similar vectors. And I'll skip most of my verbiage here and just say the danger here is that we're using language very sloppily. So the word semantic, for example, is being misused. we are approximating semantics. It's not actually semantics, it doesn't understand things. So what can we do with it? The question is it useful, not is it semantics? Okay. All right, skip. So what's the conclusion of all this? Well, we start off with the idea that prediction is hard, and sure enough, prediction is hard. But one of the things that's funny is that many times the predictions are about the technologies as it's conceived. And many times you get a sequence of derivatives of the technology which eventually lead to something useful, either with the central part of the software, what it was designed to do, or something peripheral. So maybe the biggest effect of Maxima wasn't that it could do symbolic algebra, it was that it familiarized people with the idea of symbolic algebra. Maybe the biggest effect of MathCAD, I mean, who's heard of MathCAD? It's, no one's heard of Math, well, a few people, okay. So its biggest effect was the notebook interface, which everyone uses now. And the other thing about predictions is that many of them, what's missing is not the correctness of the prediction, but the timing of the prediction. And that's where I really have no clue how to think about it. I have no clue how to think about when something is mature. When is the technology going to take off? Sometimes the hype cycle correctly predicts the future, sometimes it doesn't. So you have to embrace uncertainty. Work on what's fun and interesting. Give it up when it's no longer interesting or it doesn't seem to be fruitful. Try something else. That's what they call pivoting in the startup world. Work for the minimum viable product, a term which, by the way, I tried to find the origin. It's as recent as 2010. I thought it was older than that. Develop the minimum viable product and see what users like. Users are unpredictable. You don't know what users are going to do until you put something in front of them. Build prototypes. That's what I have for you today. Actually, it's half of what I have for you today. It's half of what I have for you today, but.
Maybe we can talk to you during lunch. Quickly, just one question.
How do you enjoy Vienna?
Vienna's fantastic. Vienna's fantastic.
Okay, thank you very much.